Welcome to HC26. Keynote 1. Power Constraints, from Sensors to Servers.
Welcome back. We have our first keynote of the conference coming up. I'd like to introduce Mike Muller. He is ARM's CTO. He was actually on the technical side when ARM was founded. He was actually a founder of the company. But then shortly after the company started, he switched over to the marketing side. And he then recently, in 2000, took on the title of the CTO. And we were just talking about what his job involves. It's still a little bit of technology, a lot of business strategy. And he is really the best presenter to have us give an overview of where things are going with Internet of Things. We had a great tutorial on IoT yesterday. And Mike is here to give us the big picture perspective. Here we go, Mike.
Thank you. Good morning. So I was given this title by a colleague of mine who originally said he'd give this keynote. So I've tried to fit my presentation into this title. But I'd like to start, if you wouldn't mind, with a little history, because I have some emotional baggage that I'm afraid I'm going to have to unburden at the beginning of this talk before we can proceed. So I'd like to go back to 1983, which is when I started work on the first ARM processor project. And of course, in those days, I was reading books, buying vinyl, and there are people both old enough and young enough to know what vinyl is. And computing was all about home computers in those days for me. And on a business world, it was still a lot of compasses, paper. If you were a banker, maybe you had the world's first mobile phone, but I don't think anybody here probably did. Lotus 123 got launched, and the infamous Osborne. And as you've just been told, when ARM got spun out a few years after that first development into a separate company, I became the VP of marketing. And this was my attempt at the time to explain how what ARM did was a little different to the rest of the industry, because in those days there was a whole RISC versus CISC debate, and we wanted to say we were different from both RISC chips and CISC chips by being low cost, low power, and optimized for a different point than the rest of the industry. And the emotional baggage came from the second big presentation I ever had to do, which was at Hot Chips in 1992. And I give credit to the organizers in that they had tracks on low-cost processors, and they had a little track on low-power systems. But I came away from that knowing that I was the odd one out from the whole group, because everybody else at the conference, while they were talking maybe about their low-cost or low-power solutions, they also had the real thing. They had their big chips and the hot chips, and we just had our little thing. And so I kind of left that conference feeling I was a little bit of the outsider, and it's taken 20 years before I'm prepared to come back and talk to Hot Chips again. And looking at the agenda for this year, I see there are quite a few ARM-powered server track with, I think, 3 different ARM-powered server presentations. There's a whole bunch of, obviously, mobile stuff on ARM. There was some IoT stuff at ARM. So I think now it's safe for me to come back to Hot Chips. And I'm hopefully not quite so much as the little timid outsider that I was 20 years ago. So with that kind of cathartic experience, I'd like to move on. And the year after, 1992, 1993, for me turns out to be the tipping point for what ARM was about, and I think the electronics industry in general. We had the first real web browser, first DVD, which was video going digital, kind of after MP. The Game Boy, which was, the transition to mobile as being one of the driving form factors for entertainment. Obviously, the first ARM-based GPS system. The first real ARM-based consumer product, the Apple Newton. Can't say it was a glorious success for anyone involved, but it was our first kind of visible product. First GSM consumer phone, and the first IBM ThinkPad. And that's kind of the world going mobile. Now, of course, if you'd been paying attention in 1993, you'd have put all your money into Amazon, which was founded in 1994. So early mover advantage there. And if you run this forward 10 years, you get to, for me, when the world went unplugged, you had now consumer GPS as being commonplace. We all had BlackBerries. It was doing all of our mobile computing requirements, and iTunes got launched, which is the kind of final place where you've unplugged yourself from a media perspective. But of course, if you were paying attention, you'd have put all your money in Facebook. So, run forward another 10 years and you get to the Galaxy, seems a little distorted, Galaxy Note. And for me, that was kind of the epitome of mobile computing. I do a whole presentation comparing it to the first Apple Newton. It's about 2 millimeters wider on both sides for the display. And I like to say sometimes I've gone from a black and white display and a color logo in those days for the Newton through to a color display and a black and white logo on the Samsung phone. There's 30 years of my life. How much have I achieved? Same user interface, touch, same idea about apps, internet access. I'm not sure what's really changed, but apparently it's a whole new industry. So if you take that as the kind of, top right, high performance for mobile, I always like to look at the other end of the spectrum and like to go and have a look at the bottom left. So, what are the small things that we do? So if you go back to a classic voice-only, SMS, hardly any data phone, what was I saying about that in the past? Well, 2000 again, as I became CTO again, doing presentations, and the world was talking about convergence. It was how we were going to take these dumb, simple phones, we were going to join it to PDAs and computing and communication and media, and we were going to have these converged products. And it's all about convergence. That has since turned into the smartphone, but in those days it was all about convergence. Now, of course, being me, what I was talking about was divergence, and I watched a film on the plane on the way over called Divergent, and apparently I am a divergent person having watched that film. And what I was interested in wasn't this coming together, this pulling together of all of these different form factors to this single device. It was how communications was actually enabling a whole load of devices, and we were going to have divergence in what products were, not convergence. And so it was all about Bluetooth, which was launched in that year, 802.11, which has spawned so many different standards from that, and the whole cellular data industry. So I was arguing you were going to get the embedded dial tone, and for 10 cents, you'd have any product you want would be wireless enabled. Now, I got some of that wrong. I think some of the business models around SIM cards, access to data, pricing, patent pools around that have meant that you don't have 10-cent hardware for true cellular access at that kind of original, very low data rate GSM point. But I think you get close to it. I think you see today Bluetooth LE-enabled devices everywhere. You can start to put that kind of communication for just a few cents into any device you want. So I was looking in those days at what was a simple GSM baseband, and the leading edge was half micron. Those of you remember microns? So half micron GSM. And I was predicting this 10 cents was going to be when you could scale that down by, an order of magnitude to 0.05 micron, so 50 nanometers to you and me. And I thought, well, how did I do with that prediction? So I was talking about a factor of 10 process improvement. That's 2 or 3 Moore's Law's generation, 6, 7, 8 years, depends how you want to argue it. So I looked through all the presentations I've ever given until I found one where I was talking about, 0.5 going to 0.05 micron technology. And I found this one, where in 2000, I was talking about 2008 technology, when 45 nanometer was the mainstream. And I was arguing that the industry was facing a fundamental problem, and that if you took a chip at 45 nanometers and you said that is ISO power, so take that as what your power budget is, and run it forward into the future to 28 and 11 nanometers, you could see at that point that what was happening to voltage, what was happening to process geometries and the capacitances meant that you weren't going to be able to run all of the transistors you were going to get in the future at the same power point that you had today. And that the scaling of performance and power and area were no longer going together, and that in the future we'd have dark silicon. Because if you had that fixed power budget, you wouldn't be able to light up all the transistors on your chip. Now, obviously I got it wrong, because you look around and there are products shipping today on 22 nanometer, and they are the same size as the old chips, and they use all the silicon, they use all the transistors. I got it wrong. And that kind of troubled me, because I couldn't possibly have got it wrong. Can't have got it wrong. So I went back and you look at the data, and it's quite simple. If you look at, and this is a sample of kind of real SoCs for the mobile industry over time, you can see what has happened to the power budgets. And lo and behold, what used to be 100, 200, 300 milliwatt power budgets for your SoC have turned into about 2 and a bit watts maximum. There's my dark silicon. There is the factor 4. What's happened is we haven't gone ISO power on those original chips. And if you think about the battery life of some of those early phones through to what phones became for a period, you can see it wasn't ISO power. And if you put tablets onto it, well, it's quite clear that the power budgets are even more than that. And what's happened is the mobile industry has grown into the thermal limits of the platform they're in. So the thermal limits of what your mobile device is now set what the power budget is. That's why tablets are bigger, phones are less. And so we do have, I believe, a dark silicon problem coming, because now we've hit those thermal limits. If you go back, and I'm going to make my predictions, here's 2014, it's 28 nanometers. And you can look at the device physics, and you can run it forward, and you can say, this is what's going to happen at 16, this is what's going to happen at 10. And you look at it, and by 10, if you want ISO power on that chip, you're only going to be using maybe 40% of the transistors. And we can't play the same trick of changing the power budget, the thermal limits of the devices are set. So I think, we're going to be stuck with this. And the question is, how do we actually get to use those dark silicon transistors? Because we know as designers, we're going to want to do things with them. The software guys are going to want us to have them there. So we have to find techniques to how we're going to make that work. So there are some possible solutions, but it's still all about the power. It was about the power when we started ARM in 1983. It was when we created the company in 1990. It's all about the power. It always has been, and I'm saying it always will be. So nothing's changed there. Now, I quite often talks about my favorite product, and this year, this is my favorite product. I need to declare an interest because I'm non-executive director of the company that makes this, so it's shameless advertising. What it is a charger. And I'd like to just show you what's inside it, and we kind of take it to pieces. It's about this size, about twice the size of this, and it's a fuel cell. And for those of you who want to know how that works, you start with a cartridge, which has hydrogen contained in a chemical hydride, and you have a charger. Now, it's okay, I can talk about this product because there is an ARM processor that controls it. And you have a stack of fuel cells, and that stack is made up of a set of plates, and if you explode out a single plate, and this is the same technology that you get scaled up into fuel cell cars, so it's exactly the same technology with kind of a bit of Moore's law shrinking going on. So let's have a look at that single plate. And all the magic happens at the proton exchange membrane. So that's where the magic happens. And to make this work, you blow oxygen, otherwise known as fresh air, through a fan and over the cathode, which is actually where all the hard work happens. And at the same time, you open a valve and you let out hydrogen, and the hydrogen comes across to the PEM, proton exchange membrane. There the magic happens, and you get hydrogen ions and electrons, and of course the electrons go in the opposite direction to the circuit. I've never understood why we got that backwards, but we seem to have just confused children. And the result is you can generate electricity and produce water, so you've got a nice, clean, refuelable system that only generates water. Now, if this technology shrinks, maybe we can fundamentally change what some of the power supply issues are in portable devices. But whatever we do on battery technology or fuel cell technology or solar cell technology, we're still left with those thermal limits. They're not going away. That's the real mechanical world that we live in. So however much we fix one side of the problem, we're still going to be left with those power thermal limits. So the obvious solution to this dark silicon problem has always been heterogeneous computing. Take the original ARM phone, first ever GSM phone we shipped with Nokia. It was a heterogeneous system. It was an ARM plus a DSP. And it was lovingly done with manually partitioned C and assembly code. It was the most efficient way of undertaking the computing problem. It's a heterogeneous solution. Take that Galaxy Note, top right. It's a heterogeneous solution. This time it's an ARM with GPU. And I kind of argue I'm not sure the programming model has changed at all. It's manual partitioning, it's C++, and it's OpenCL and RenderScript. And OpenCL and RenderScript is about as close as assembly language programming as you can get. You know, I'm not sure the world's moved on, but the numbers have all got bigger, so it's a glorious top right solution. So heterogeneous compute, a good way of solving the dark silicon problem. Create accelerators that are optimized for the task at hand. Don't have them turned on all the time, only use them when they're there, so we find a way of using those dark silicon transistors, but they're not going to all be on at the same time. So let's look at some kind of drivers for heterogeneous compute. Now, obviously, in the mobile world, one of those drivers is mobile imaging. It's all about how to make you better photographers than you really are, and you do that with magic. So you have to find people's expressions, you have to cut them out, you have to stitch it together, you have to then actually apply the makeup and do the blemish reduction. All of that is really computationally intense. And, you know, it's around 100 gigaops per watt if you're actually going to perform some of those extreme tasks. Another driver for this kind of technology is all of the advanced driver assistance you're seeing for lane detection, hazard detection, parking assistance, all of those things that are going to make cars safer before you ever get to the fully autonomous systems. It's actually a very similar computational problem, slightly lower gigaops per second, not because you need less, but actually because what you need to do is provide a more reliable system. You're talking about dual and triple redundancy. You've got to actually get ASIL D compliance, and that costs you transistors and complexity to get those sort of compliance systems together. So actually the number of gigaops you're going to be able to do in your power budget is less. And then ultimately, you've got things like high-performance compute. We've seen some of the hotter chips this morning. And if you look at that, if you're going to do your exaflop at 20 megawatts, again, it's all just a power problem here, it's 20 megawatts, and you decompose this and you look at the numbers, you end up with exactly the same answer. It's around 100 gigaops per watt is what you need to provide at the core if you're going to stack lots and lots of them up to have this 20 megawatt solution by the time you said a third of that storage, a third of that is compute, a third of that is interconnect. So they all end up being comparably the same problem, even though one is mobile and the other is the extreme of computing. Simplify it down, you get to about the same performance points. So people have talked about using GPUs for GPU compute. We do it with our range of graphics cores. And the reason is you can build good, efficient microarchitectures with a GPU. You don't have to really worry about dynamic scheduling. Most of the GPU code runs in a straight line, so you don't really need to worry about branches, so you throw away all of that complex branch prediction logic. You don't do register renaming, you don't do results forwarding, you actually end up making really simple cores with long pipelines, and you can lower the clock frequencies. And the way you make it all up, of course, is at the end of the day, you kind of go, let's stick lots of it together, you have multi-threaded, and then you have multi-core solutions. And from that, you can get high performance. Now, what you're doing is just reducing your ALU control logic ratio. You've got lots and lots of compute, you've got hardly any control, it's more efficient, so you get better ops per watt at the end of the day. And, you can do short vectors, expose that to the programmers, and it's a threading approach. So, is it all good news? Well, No. If you look here for the last few years at the top 500 HPC systems, you can see this kind of interesting little spike. Now, that's because that was a GPU-based system. You get an incredible amount of gigaops per core at that point, but it's not actually that easy to program. And if you can't program it, you can't use it, maybe it's just a fashion thing. And that's what I think a lot of people forget about. You know, it's the system stupid, it's the programming model, and in the real world, the real world isn't full of hardware designers. The real world is unfortunately this fantasy world of programmers. And they're who our real clients are, and that's the world you have to make easy and approachable to use, because if the programmers can't use it, the hardware doesn't get used. So how do you actually go about making something like this that might be easier to program? Well, we've done heterogeneous compute between GPU and the ARM core. That's the classic heterogeneous thing. We've taken it in a different direction. We kind of went big, little. How about homogeneous architecture heterogeneous compute? You have big CPUs and little CPUs. And you dynamically decide what's the workload. Should I run it on a big core? Should I run it on a little core? You can make the little cores more efficient, so you can have lower power operation from the little cores. You use the big cores when you want. And so the obvious question is, you know, can you be a little divergent and push this a bit further? So what happens if you actually build a massively threaded machine that looks like an ARM? And the answer is you can. The upsides are you can program it in C++, you can use OpenMP, it's a classic programming language and paradigms, it's the same binaries, the same ABIs, it's got familiar tools so you can make it less threatening for programmers to approach it. And you have exactly the same memory model, so there's an awful lot less overhead for doing handover of work between one task and another. And you don't need to restructure or mark up what your memory is to actually be able to use it. So the question is this actually any use to anyone? Well, if you look at it, you can take some benchmark, and we can have an argument later about are these benchmarks relevant, but you know, they're good enough for what they are. Take it and run it on a classic ARM processor in C, factor 1, effort low. Just write the benchmark, compile it. If you work hard, you can optimize it for the SIMD engine that's been built onto the side of ARM over the years, and you can push that performance up by a factor 15, maybe a factor 20, 25, by putting hard work in, manual partitioning, manual polishing of the assembly code and intrinsics, and you can get a reasonable performance increase. So what happens if you then just take that code and recompile it without doing any work at all for this massively threaded machine? Well, the answer is you get all of that sort of improvement for no programming effort. What you've done is you've spent an awful lot of transistors. They're quite power-efficient transistors, and it's only suitable for certain codes. It's not a general-purpose engine. But going back to my dark silicon problem, I think you'll have transistors lying around that you can spend your money on. So that's what happens if you just do the lazy job of compiling it. Obviously, if you put in a little bit more work, you start unrolling the loops, you start doing more sophisticated polishing by hand, you can push it maybe over a factor 100 in performance for what you get. It maybe doesn't take you all the way to what you have with the full-blown GPU compute, but you can get pretty close to it for very little effort. But what you've built is a very specific accelerator. As I said, it doesn't take branches well at all. There's very limited code you can run on it. But if you go back to some of those drivers and the real performance needs we'll need to make those lane recognition and hazard detection systems work, it'll be worth putting investment into some specific codes in order to be able to extract significant performance. So I do think when you look at system architecture, you'll find different ways in which you use transistors to solve that problem. Now, obviously, you've got to manage the power in these systems. There's a whole lot of work to be done in how you do the control automatically of does the workload run on the big core, does it run on the little core, what voltage, what frequency, when do I switch it, and you do all of those changes in the Linux scheduler, and it works for free. Extend that, you can make it work for GPU, you can make it work for any accelerator, and you need to extend that to be able to get the most out of your thermal limits. And to get the most out of the thermal limits, you need to be able to decide which of those accelerators do you actually want to run the workload on, and what is the predictive power model of that accelerator, so that you make sure that you stay within the thermal limits, and you don't have to keep saying, well, I'm running towards the limit, I'll stop and come back. You've actually predicted, because you understand what the workload is. Now is not the time to switch over to the big core, because you're actually near your thermal limits. As soon as you get there, you're going to have to start throttling it back, so there's no point making that switch. You need to stay where you are because you're within the thermal limits of the package. So you have to put that whole hysteresis of the thermals in to make it work. And if you do that, you can actually get a more efficient system. So you can extend this out to any of the kind of accelerators that you might have in that chip, because I think in the future, you're going to be spending more time worrying about what those thermals are, how do you manage, how do you determine which your workloads, which goes where. So it's still all about heterogeneous systems. Nothing's changed. So we've seen some very big chips that run very hot and run very fast, and you obviously in those worlds have to worry about aging and wear out. Do you need to worry about that in mobile systems, or is it just a problem for the big boys? And I'm afraid the bad news is yes, you do need to worry about it. Because while it's true those aging effects all happen at high voltage, high temperature, high frequency, what I've just explained to you is a world where you're doing dynamic voltage frequency scaling, and it turns out that the wear-out effects that you get at that high voltage, high frequency point move your threshold. You then dial down the voltage and you run at a low voltage, you've moved the threshold. What is a small effect at a high voltage actually becomes a more significant effect when you've dialed back the voltage and you're running at low voltages. So a small VT change for your high end, which maybe wouldn't affect you because it's not an extreme system, you probably wouldn't need to worry about that wearing and aging effect, does actually become relevant as you turn down the voltage. So sorry, yes, in the future, you probably are going to have to worry about the whole BTI and other models of how you do that. So, we've done some work on that, and if you look at a kind of mid-sized embedded core, and you just run it at a modest temperature, modest voltage for a few years, which may be the lifetime of that product, and then try a different set of benchmarks going from, MP3 as the simple, trivial use case at one extent, all the way through to video decompression at the other. What you discover is, yes, there is a timing degradation, and it can push close to 10% at the high end. And that number is big enough that you have to start thinking, do I need to worry about that? So I'm sorry, I've just made your life harder. Things will get more complex into the future. The other question to ask is, is it safe? So if you look at SoCs and the fit rate failures over time, if you look at unprotected memory, that's been growing and growing and growing. Of course, there's a simple solution to that. It's primarily ECC. It's physical interleaving, where you can actually turn multi-bit cells spread across. So physically, you can turn multiple bit failures into single bit failures. You can do all the temporal scrubbing effects. We've effectively found ways to reduce the problems of SIR failure as the process nodes have generated more and more transistors. However, I don't think there is any good way of globally solving unprotected logic. And that is now what's starting to dominate the effects, well known in the server world. And the question is, how does that play through to the other sorts of systems you're going to build? And, the good news is, if you take an ARM processor and randomly inject faults into it, 94% of them have no effect whatsoever. I sometimes kind of wonder, well, what on earth was the logic doing there that I didn't care what happened to it in the first place? But that's a kind of design review question. But you're still left with that, that 6% that does actually matter, and you need to do things to fix that. So how are you going to fix those failures that actually matter? Well, the answer is you can protect any particular flop, but you can't protect all of them, because that's going to cost you too much in terms of performance, power, area. So, you need to develop a flow that takes what your workload is, pushes it through the design, does the simulation, and you can actually identify there are flops that are more critical than others. Not all flops in a design are made equal. There's a whole lot of logic that in a branch target cache, if you choose the wrong answer, it doesn't really matter. If you go to the wrong address, it does. But the logic that selected which address to go to doesn't matter. You can allow a failure there as long as you end up at a valid address. Turns out to be the wrong one, didn't matter. So different flops actually have different levels of importance. Lots of them are simply masked, and you can prove they're masked. They don't matter. So you can identify the critical flops. You can then go back and say, for those flops, I can put hardened flops into. I can reduce the risk of a failure for that. And I can iterate on that in an ECO way, so I can do it towards the end of design to actually make this flow tractable. It's not a kind of top-to-bottom problem. You can ECO at the end of the design flow. And then you can achieve your target. The challenge, of course, is that this is a trade-off of area, power, and failure rate. And people are going to have to start worrying about what is that trade-off you want to make? What is your power budget? What do your customers expect from the lifetime with a product? And who are they going to blame when it crashes? And, we're maybe quite fortunate in a lot of mobile applications. It's clearly the software's fault. Everybody knows it is, okay? Not true in all applications. Not true in my driverless car. Not true in my pacemaker. So there are different times when you really do want to worry in a different way about what that is. And it's not just all about those 99.999% high reliability systems. It's something you're going to have to worry across a much wider spectrum. So whatever system you build, when I was at university, I was taught it's all about the main memory, stupid. That is where the bandwidth problem is. That's what it's all about. Last year, I was publicly complaining about where the world was going in terms of memory standards. If you looked at the graphs I was talking about last year, you had the top line, which showed what the theoretical peak memory bandwidth was from DDR systems, and in orange was what would you actually get in a real-world system with a 64-byte line cache remiss and load rate, and it was nothing like the peak bandwidths. Now, you could say, well, that's fine. Other people are using the peak bandwidths. Why complain about it? And the reason I was complaining about it was, as a mobile customer, I was paying for that because those memory systems were not power proportional. They were designed and were consuming power optimized for the peak. If you actually were using a lot less, you weren't getting the scale in power that you should have expected because you were carrying the burden of those high-performance systems. So I was arguing that we needed to find a different way of addressing what memory interfaces were going to look like for future mobile systems. And since then, we've engaged with our ecosystem, still obviously doing stuff at the very high performance end with Hybrid Memory Cube, but also have started a working group in JEDEC. I would encourage you, if you care about this, to get involved. Because I think it is critical for the systems we're going to be building in 5-6 years' time that we can actually build what we want. And so I'm interested in 2018 and beyond, how do we focus on usable bandwidth, not theoretical peak bandwidth? And how do we do that with some abstracted packet interface that allows us to take one step back and say, I don't care what the memory technology is, I don't care what optimizations you've put in there, I can build something that's power proportionate for the system and bandwidth that I'm using. Now, obviously, one size doesn't fit all from an implementation level, and so while there will be an architecture level that's common, you actually need probably 3 different performance points, which scales from the kind of the mobile 60 gig at 1.5 watts through servers at maybe 150 gig with 10 watts, all the way to extreme networking, which is probably the real performance driver at 300 gig. And budgets off to 15 watts. They will have different physical interfaces, how many pins you're prepared to use, how much power you're prepared to push into those pins to drive them. And we need to have something that solves that problem. So I would please encourage you to get involved in that JEDEC group, because I think it's the most critical thing that we collectively can do to change what the power footprint is of devices in the future. So always has been, it's still all about the memory. So talked quite a little about the top right, servers, fit rates, reliability, aging, wearing, all of that stuff. How do we scale this all the way down to the square millimeter tiny embedded systems? So let's have a look at some of the scaling challenges. Now, some scaling is easy. If you just take a ARM7 CPU core solution, 1.2 gig at around 2 and a bit square mil, so, your cheap mid to low end phone. You can scale that for free into a wearable just by changing your synthesis targets. Don't push it to 1.2 gig, just aim for 500 meg, and you halve the size of the output. So you can get scalability by just backing off from what you're actually trying to do. You can push that a bit further and say, well, actually, I want to do a really optimized one. I'm going to take it down to a uni-core rather than dual-core. I'm going to lovingly polish it, and you can take it down from over 2 millimeters to, under a half a square millimeter, all with the same RTL. So we can scale ourselves a long way from mid-range mobile, getting closer to those tiny, tiny cores, but that's obviously not enough. It's got us factors of order 10 improvement and significant reductions in leakage, power. But of course, what really matters in this, to some extent, is what process do you pick. If you redo it all for 40 LP rather than 28 HPC, chip gets a bit bigger, but you can significantly reduce by orders of magnitude what the leakage is. So again, implementation really matters, your process choices really matter. You do all of that with one block of RTL. But that's obviously not going small enough for some of the devices we want to build. So how do you build things that are, 0.05 of a square millimeter in size and still get them code compatible, all the benefits of being ARM? I have to kind of say that every now and then. Well, the answer is you have to take a completely different microarchitecture approach. You have to throw away your caches, your MMUs, and build a tiny focus core. So I'd like to have a look at kind of what does it take to build some of those tiny systems with an ARM core. So how do you get efficiency in those? So here's a test chip we've built. It's a classic test chip. It's got an apps processor in it because any demo you want to do, you need to run kind of apps software on it. So it's a 250 meg system with a Cortex-A5 in it. And then it needs a comm subsystem, and that's obviously a Cortex-M0, and it's maybe running at 40 megahertz. And then you need your sensor hub, and that's going to run 1 meg down to just a few kilohertz. The interesting thing to note on this picture is the comm subsystem and the sensor hub subsystems are almost identical. And one of them is 4 times the size of the other. And I'd like to touch on why, when you actually are pushing the lower ends of performance, you actually have an area trade-off to make. And here, in this test chip, it's about a factor 4. It's extreme, but I'll explain why. So it's all about how you run directly from batteries. So this is build a chip that has all your voltage regulation done on chip. You don't want to push that off chip. So it's got to go from 1.2 volts down to 0.2 of a volt. It's all on chip, and you've got this direct battery operation. So to build that low power system, it actually took 12 different power domains. You look at it, you want to run really low power, you have to be able to slowly segment your memory, switch off sections of your memory as you go. You need to have the debug, the test, everything in a different domain. We ended up with 12 different power domains. I'd just like to point out there's kind of like 2 functional blocks in here. It's Cortex-M0, and there's also a hardware 128-bit AES engine, just to show from a research perspective that all the power techniques and design techniques work whether you're talking about processors or just random logic. This isn't a processor thing, it's a design issue. So that's the system. And you discover that as you take the voltages down, it's obviously SRAM that contributes the most to your standby and retention powers. That's why the SRAMs in the smaller system are about 4 times the size of the SRAMs in the 40 meg system, because that's the only way you can get them to work at 0.2 of a volt and not leak. So your SRAM design really has to be optimized for what your lower power points are. Things like level shifters, you're really susceptible at those low voltages to what your variability is. So you have to have good control of that. And the same is true of things like your power gates. Again, it's a bit like the wear-out effects that happened at high voltage, but when you run it at low voltage, become really quite significant. Same's true with power gates, because at your very low voltages, inefficiency in your power gate is voltage droop. The voltage droop at that point directly turns into frequency. Frequency turns into operating time turns into leakage, so your leakage ends up being directly driven by how good your power gates were and how efficient they were. So there's a whole bunch of design things that become much more critical than you'd first think. And then finally, the EDA tools don't help you out because they go in the wrong direction. When they're used to a world in which RC dominates, and then it turns out the gate delay dominates. So the whole things they do to try and get you timing closure at your very low voltage take you in exactly the divergent operation to where it is to get closure when the whole domain has changed. So again, you need to be aware of that and push it in the right direction. So, real silicon, real chips, obviously you get these classic curves that show you how, if you take milliwatts on one side, frequency on the other, scale your voltage, and see what happens. And if you want that minimum point, that minimum power point, you're running at 200 millivolts. And it's, 1/6000th of the power. It's maybe 1/3000th the frequency. It's the right place to be for energy scavenging. But if you, of course, want the minimum energy point, you have to put in leakage, you have to put in what your runtime is, and at that point it turns out that obviously the right place to be is near rather than sub-threshold, and your minimum energy point then is probably around 400 millivolts. And you get, 1,000th of the energy for 100th of the frequency. It's an interesting place to be. So energy scavenging moves into maybe battery operation at that point. And the thing is, it's entirely possible to build those systems. You can be lazy, of course, and if you're lazy, then you just do it around 600 millivolts. You get about half of all the savings, and you really don't have to do anything, and if you push the tools, they'll do it for you for free. So, again, there are things you can do if you even aren't prepared to put any hard work into it and stay around 600 millivolts. So, it's great. What are you actually going to do with all of this? Because as I said earlier, the real world is full of programmers, and programmers are not really interested in these millivolts and milliwatts and whatever. They have a problem to solve, and for them, it's, I need Bluetooth, and maybe that's an 8 megahertz point. It's about what you need to run Bluetooth LE. Or maybe you just want to do general purpose MCU work. There's lots and lots of things you can do with a megahertz. Or maybe you're right at the bottom and you are building a teeny tiny sensor chip and all it needs is about 100 kilohertz to do some very, very simple comms and computation. And you can overload onto that then what are you going to use? And I'm being counterintuitive here. I'll put energy scavenging at the top. If you're alive, and you're not wearing too many clothes, you can maybe get that 5K, 5-degree thermal gradient, and you can therefore probably generate 300 microwatts. So it's enough to actually run Bluetooth LE for your Bluetooth-enabled bandage that is getting its heat from you. It doesn't need to have a battery. You can just about do that. You're maybe running an MCU, and that's 5 years continuous operation at 1 megahertz off a standard coin cell battery. So you might ask, well, yeah, but I don't need a megahertz all the time. My duty cycle's probably, 10 to 1? What would happen if I do that? I'm going to get 50 years out of it. That's great. I can install it and build it and forget about it. And of course, the answer is, no, you can't. Because the self-discharge time of a coin cell is about 10 years. So at a 10 to 1 ratio of that 1 meg microprocessor, you actually get about 9 years. And that's the best you can do because the battery's going to be flat in 10 if you do nothing at all. So building battery systems, again, it's a system problem, stupid. You have to look at what your power source is. You have to look at what its real internal discharge is. What system can you really build? You might go, you know what, I'm just going to run my microprocessor flat out continuously. It's no point in worrying about all these duty cycles because what's the difference between 5 years and 9 years? So you really have to look at your system, and it's maybe not obvious what optimizations you should be taking when in order to build that lowest power system. It might be more efficient to run it all the time at a lower voltage than spend lots of effort to work out when you're power gating it, when you're running all of these different things. So some of it becomes counterintuitive. And then ultimately, you may end up with something that's running in that tiny indoor sensor. I'm always amazed at what you can actually do with photovoltaic cells. And for maybe 4 square millimeters, you can just about run Cortex M0 at 200 millivolts and run it continuously in indoor lighting in that kind of 100 kilohertz range. So what I've tried to say is whether you're building really small systems, whether you're really building very, very big systems, it's still all about the power, always has been, always will be. It's all about building heterogeneous systems, and those embedded power-constrained mobile phones have been heterogeneous systems from the beginning. That's what all systems look like in the end. And it's still all about the main memory. Nothing's changed there. I think if I come back in 20 years' time, and talk again at Hot Chips, I'll be saying something that will be slightly different, which is, I think, is in the future, rather than looking at this kind of bottom-up hardware world, it will undoubtedly be the cloud that actually drives device requirements. It's going to say what is the connectivity that you need from these devices. It's going to set the programming styles for those devices, and we will be responding to what those needs are, and that will become much, much more important than any of the bottom-up programming that we've been doing to date. Thank you very much. Random questions?
Hi, Mike. Mike Brazzoni with Camp Marketing Consultancy, and everyone should watch out. There's a step here. So I focus on analysis at the intersection of ARM and x86, Mike, and I think you still might be the odd guy out running towards ARM's charter strongholds. There's been $365 million invested in this valley in ARM server development. Can you address running towards Intel for a moment and the utility advantages of the ARM architecture, if they exist at all, in relation to Intel? Power, performance, instruction set. What can you instill in the audience that gives us faith to continue development in this verse Intel arena? And what are the secrets as a CTO of ARM that you can instill on us here?
I'm not sure I have any secrets, and I'm not really too worried about what Intel do. They do what they do, and I'm very, very happy with that. We're focused on how we build power-efficient systems, which are, I hope I've shown, scale from small to big, and we focus on enabling our semiconductor partners to go out, build chips, and compete. They compete among themselves, they compete with Intel, and our business model is about enabling people to compete with the best solution it is, and we try and just focus on building the right technology to do that.
Is ARM the right technology for competing with Intel?
It's worked out for me so far. I think that's enough Intel questions.
Jen Lee, Huawei Technologies. 2 questions. One, probably a very simple and a silly one. Would you like to post your slides on the web?
I'm sure they'll end up...
I didn't find it in the Flash, by the way, so...
Yeah, okay. They'll end up there somehow.
All right, thank you. That was a silly question.
The video's going up, I believe,
apparently.
as well. So.
The second one, maybe you don't like either. It's sort of a follow-up from the last one. So you talk... I'm sorry. Since there are so many people, I guess we should ask anyway. So you talk all the way from sensors to handheld to servers. So I guess many of us here work on servers. So talking about 64-bit, given your expertise, as you showed already, and your level of influence, how do you think of the 64-bit ecosystem of ARM-based system?
So we only launched 64-bit architecture a couple of years ago. The ecosystem takes time to build. So there's 64-bit product out there shipping in volume, in servers. It's only just having the right cores designed for it, because there's a limit to what you can do with, take a mobile chip, repurpose it for servers. You get an interesting answer. You don't get the best answer. You do need to optimize your implementations, whether they be high performance, low power, whatever, for the target market. So that's only been happening, I think, in the last year. We've had silicon that is really targeted and designed ground up for that server marketplace. I think that ecosystem continues to develop. It'll take maybe another year or two until you can look at it and say, it's now a non-issue. We're not talking about it anymore. But I think it's one of those things that takes 5, 6, 7 years elapsed to actually develop. And we've only been doing it for a few years now.
Okay, allow me, maybe another aspect to look at the same question. What do you think could be the killer apps to promote such an ecosystem? Allow me to elaborate a little bit. Like for storage servers, we can do 32-bit pretty well, pretty outstanding power, performance, whatever trade-off from ARM. Now, any other killer app you think can really motivate us to do 64-bit?
So I think the thing about the server market in the past is it has been largely driven as a monolithic solution. Here is my server, reuse it for lots of different applications. I think going forward, it takes on more of the characteristics of the SoC market, which is more application-specific design. I think if you're doing your scale-out web servers, there are very different challenges you face in different parts of the stack, which can be optimized in a different way. Now, if you control your vertical software stack from top to bottom, you know where those points are, and you can optimize them differently. If you're trying to offer a generic compute solution, then you don't have that opportunity to be able to do the specialization. And I think the server market is also fragmenting and blurring between what's server, what's networking, what's storage. Those are actually moving as the cost of, the cost changes about where do you do your compute, where do you have storage, and you're moving compute towards storage, and you're moving compute into networking. So I don't think there is one killer app. I think there's actually a whole lot of different market segments that have different solutions.
Thank you.
Hi, Fred Weber. I was really pleased to see your multi-threaded machine that you showed from research. It looks like it could be really interesting, but a little surprised that you got lower performance than a GPU. Can you explain why that would be? Is it a fair comparison, same amount of silicon and so on? A GPU has a lot of crap that doesn't help you with the matrix multiply, and you should be able to design a machine that does better than it.
Yeah, okay, so that is strictly an implementation reality, and it's saying when we looked at what we thought was the right kind of compute size performance trade-off for that engine, that's the limit we put on it. The GPU was already bigger than that, because there's a whole load of GPU-related workloads that pushed you further. So the GPU is bigger and therefore got better results. And we were trying to just be fair comparing what we designed. And I didn't show you, I admit, because I don't want to do that just yet, what the die sizes are. They're not the same size, and that's why they're different.
Right, but as an architectural solution, you think you'll get higher matrix multiplies out of that per square millimeter?
If you targeted ISO area, yeah.
Hi, Thomas Summers. So you talked about the CISC risk wars of the 80s and 90s, and it's quite clear that risk won, even if the x86 instruction set and others are CISC at a high level. The actual core implementations have gone to reducing complexity. But over the past couple of years, ARM's instruction set has grown. The actual core implementations have added a lot of features, and in my personal view, I think it's a lot of feature creep. Do you think that that's going to continue, or is there, like, it's kind of changed over the years from going to the bare bones, the minimum you can do to be able to get work done?
So, of course, part of the trauma I had back in '92 is I was standing up going, well, I've got this RISC processor, but we do load store multiples. We have conditional execution. We had lots of original features of ARM which people frowned at as not being RISC-like concepts. So I think we've always had things in our architecture which weren't pure RISC. Has the instruction set got richer over time? Call it feature creep if you want. Yes, that's one reason why we have, ARM profiles. We have application, real-time, and microcontroller, and those profiles allow you to select some of those features because you don't want some of the things that are great for memory ordering and consistency and memory barrier operations when you're building tiny microcontroller. So there is some balance to be made between adding features and still maintaining a core architecture that you can segment to make it scale.
Thank you.
It is 12:30 now. Mike, thanks for your time. Thanks for answering questions. Mike,